Durvankur.
So, welcoming all to this session on a webinar on how long would an EV battery last. So, this webinar is being delivered by Dr. Rutuj Deshpande. I'm getting an echo from somewhere. So, some basic rules before we start. Everyone should be on mute. Let me give you a brief intro about Dr. Rutuj. He is a battery scientist currently working as Deputy General Manager in Sterling and Wilson Private Limited, Pune. He is heading a team to design grid scale energy storage solution. And he recently has returned to India and joined SWPL. Rutuj also worked as lead battery engineer with Ford Motor Company in Michigan, where he was involved in designing automotive traction batteries for more than 15 vehicle programs, including electric F-150, Ford Mach E, Ford Fusion Hybrid, plug-in hybrid, etc. Additionally, he is also a visiting faculty in Department of Chemical Engineering and Material Science at Wayne State University, Detroit. He has received his PhD in Chemical and Materials Engineering from University of Kentucky and performed postdoctoral research at prestigious Lawrence Berkeley National Laboratory with lithium-ion batteries, being his primary area of research. Rutuj has authored 12 journal papers, 11 patents or patent application trade secrets in last 12 years of his battery research. Rutuj's research on battery degradation modeling is highly recognized in research community, totaling more than 1100 citations till now, and various international forums with awards such as Graduate Excellence in Material Science, Diamond Award by American Ceramic Society, Person with Extraordinary Abilities by USCIS, High Tech, High Demand designation for critical role in area for Ford's strategic priorities, Ford Recognition Award 6 times from Ford Motor Company, etc. Rutuj is reviewer for several well-known scientific journals, including Proceedings of National Academy of Sciences, Journal of Electrochemical Society, and Journal of Power Sources, etc. So I'm handing over to Rutuj now, and I guess we can start, Rutuj.
Hello. Hi everybody. Can you see my screen or not? Is my screen visible?
Yes.
Okay. Durvankur for everybody for thank Device Electronics for giving me this opportunity to present some of my work or some of my perspectives on battery degradation and battery life. And I would also like to thank everybody who's attending the seminar, taking out their precious time. First of all, with the COVID stuff, I hope everybody is staying safe, staying at home, and staying healthy. Uh, Coming back to the topic, how long would an EV battery last? That's a question that has been asked to me frequently for last 12 years, and I'm trying to answer it with exploration of physics, with the different aspects of physics in a cell, in an electrode, at the atomic level, at the cell level, or at the pack level. Um, to give you my background, I'm currently working as a deputy general manager at Sterling and Wilson's Private Limited in Pune. I'm also adjunct faculty in chemical engineering at Wayne State University in Detroit. Um, I'll briefly tell you introduce my background. I did my undergrad from UDCT or ICT in Mumbai in chemical engineering. Thereafter, I joined University of Kentucky, where I did my PhD in chemical engineering with the focus as lithium-ion batteries, specifically degradation of batteries. My PhD was funded by General Motors. Thereafter, I could join the prestigious Lawrence Berkeley National Lab as a postdoc. Again, the research focus was lithium-ion batteries. After spending about 1.5 years there, I came back to Michigan and joined Ford Motor Company as a lead battery scientist, um, and worked on lithium-ion batteries for automotive applications. So various electric, hybrid, and plug-in hybrid vehicle programs. I was involved in designing of batteries, selecting the cells, selecting designing the controls, etc. I also joined as a adjunct faculty in Wayne State when I was in Detroit. And then I recently moved back to India and joined Sterling and Wilson, where I'm currently working as a deputy general manager. Here I work on large-scale energy storage solutions, specifically for grid application. As Durvankur mentioned, I have about 12 publications which are very well cited. Yeah, I recognize in the research community about 11 patents or patent applications, and there are more than 1150 citations in last 12 years to these papers. Okay, coming back to vehicle electrification, as we know, it's a buzzing word nowadays, and there is uh, all over the world there is an increase in or there is a tendency to electrify vehicles or buy new electrified vehicles. There is a famous quote by a famous scientist, and he said, "I believe that ultimately electric motors will be universally used for trucking in all the large cities." He said, "I'm convinced that it will not be long before all the trucking in New York will be electric." Some of you might have guessed who this scientist is. Just to tell, he is Thomas Edison. And it's not a very recent quote, but it's in 1914. It was published in 1914. So we have been struggling, or we have been dreaming of electrification for about 100 years now. In fact, there were electric cars 100 years ago. Uh, the fact is, in 1900, about 38% of US automobiles were electric. People preferred electric vehicles at the time because there is no pollution. There is no cranking was required, like the gasoline vehicles used to, and there was lesser noise in electric vehicles than gasoline vehicles. And now we are coming back to electrification again. So the question is, why electric vehicles lost the the market in the early 1900s, and why are we seeing more and more EVs today? Both the answer to both the questions lies in batteries or battery technology. In early 1900s, the batteries could not keep up with the fast-moving gasoline vehicles, whereas now we have we have better batteries to provide the power required for the vehicles. Then among batteries, why lithium-ion batteries? Probably most of you know, lithium-ion batteries have highest energy density among all the available commercial batteries or commercial chemistries. Um, uh, for example, lead has about 50 to 100 watt hours per liter, whereas lithium-ion batteries have around 400 to 600 watt hours per liter. Again, this data is little old. Now the volumetric energy density at the cell level has gone up to 600 or more than 600 watt hours per liter in some cases, depending upon the geometry. High volumetric and energy density, high volumetric and gravimetric power density. Power is what you would need to propel the vehicle, so to have higher acceleration or run the vehicle at higher speeds. Of course, you want long shelf life and long cycle life, so you can charge and discharge every day for so many years without really losing the capacity. So lithium ion batteries are best among the available technologies. There are new technologies coming up with higher energy densities, but they are still in research phase. Now, probably some of you or many of you know how lithium ion batteries work, but I just wanted to go briefly through it. Again, when we see uh, when we see cylindrical or pouch or prismatic cells, we have basically layers of positive and negative electrodes and separators in between in these electrodes rolled together in a jelly roll form or stacked in the stacked format. But basically, any cell or any battery has two electrodes, positive electrode and a negative electrode, and they are separated by electrolyte. Again, this diagram is not to the scale, but just an illustration. Um, so in lithium-ion batteries, we have lithium ions stored in one of the electrodes, and then as soon as lithium ions basically move from one electrode to the other electrode, and then electrons take the external circuit, and that's how we get electricity outside. So the amount of lithium that can be moved from one electrode to the other electrode would tell you how much is the energy density, or would tell you how many electrons you can take out for your application. That's basically the capacity of your battery. Typically, the negative electrodes are graphite based, either natural graphite or artificial graphite. The alternatives are silicon or LTO, lithium titanate, um, in certain cases. Typically the positive electrodes are LFP, lithium iron phosphate, NMC, or LMO, etc. So again, lithium iron phosphate or NMC, all of these are lithium ion batteries because ions are carrier of current in the electrolyte. So I see a lot of people saying LFP is different than NMC, but all of them are lithium ion batteries to the fundamentals. Okay, so coming to battery degradation, now we can basically look at it in a simple using a simple analogy. Battery, if we assume that these two tanks are like battery electrodes, so when we charge, we push water from one electrode to the other, or one tank to the other tank. So the lower tank to the higher tank, and when we discharge, we allow the water come back to the lower tank. Similarly, in lithium ion batteries, we push lithium from positive electrode to the negative electrode when we charge the battery, whereas when we discharge the battery, the lithium comes back to the positive electrode from the negative electrode. The only problem is this system is not leak proof, but it is leaky system. So that means, for example, in this analogy, the tank, we are losing water somewhere. So now each time we are cycling the water, there is small amount of water being leaked out, and we will lose that water. That means the capacity of your tank, total capacity of tank is getting reduced. Similarly, in lithium-ion batteries, the capacity of batteries would be reduced over time. For example, this plot shows there is capacity retention and years. So you start with 100% capacity, and then as you use the battery, as you cycle the battery or store the battery, there is some amount of lithium being lost. It's not recyclable anymore. It's basically leaked out, and then you would get less and less capacity out over the years. Now, what it means to an EV company? Basically, if you start your vehicle at 150 kilometer and you label the vehicle as the 150 kilometer electric vehicle, in 10 years, probably it would come down to 100 or 112, depending upon how badly your battery degrades. So you want, your target was 150 kilometers, but your user would end up driving the vehicle only 112 kilometers on full charge at the end of 10 years. So that is basically under performance. That's not good for any OEM. The second way to size it would be you target 150 kilometers for end of life, and then you have to oversize the battery to 200 kilometers. So you need much bigger battery now to start with, and your customer will get all the benefits. He will get 150 kilometers, but you are paying for the benefits by oversizing the battery. And there is third option that you just sell the vehicle and don't care about it once you sell it. Hopefully, we don't have any EV manufacturers like that here. Now, to know how long your electric vehicle battery is going to last, you would look at a cell spec sheet. Typically, a cell spec sheet that you'll receive from a manufacturer will tell you two things. One is cycle life of so many cycles for certain C rate. So 1C charge discharge for whatever 80% retention. And they may tell you about the storage life, that if you store the battery at 25 degrees Celsius, uh, the battery may last for 10 years. But the question is, if you have these specification, does that mean every battery that you have, or every battery that you will put in your vehicle would basically last for 2000 cycles or would last for 10 years? It may not be true. In reality, uh, cell life is highly dependent on the usage pattern. So if your user is mildly using your cells, you may get certain degradation. If your user is little harsher or moderately using the cells, you may get other degradation pattern. Whereas if your user is really harsh, then your cells may last only so much. So you would get much faster degradation in that case. So same cell, even though they have same specs, their life would be highly dependent on the usage pattern. So what are the parameters that really affect the battery life? Of course, duration of usage, as we talked about. Then temperature of operation. If what temperature condition is the cell or the battery seeing when we are operating it? One factor is the ambient temperature. Second factor is the battery itself, the heat generation and heat rejection of the battery. Then total throughput, how many times you are charging and discharging, so similar to number of cycles. Then cell design, is it a power cell or energy cell, and how you are using it. Then depth of discharge, are you using full depth of discharge of 100%, 80%, 90%, or 50%? Then rate of charge or discharge, is it 1C, 2C, that the rate you are using for that particular cell design? What is the upper state of charge? How much is the non-uniformity within the cell? Does your cooling system basically rejects heat non-uniformly? And external pressure, especially in pouch and prismatic case, what's the external pressure you have on the cells when you make a battery pack? That's on cell level. And then you have battery pack where you put lot of cells together in series and in parallel, and or in parallel. Now, in battery pack, there are additional factors such as cell to cell variation. Each cell is not the same. There are manufacturing differences even within a batch of cells. Then there could be non-uniformity of temperature within the pack, and there could be things like cell to cell imbalance playing some role. Uh, in the battery pack. So all of these factors would tell how your battery is going to perform, especially the life of the batteries or degradation of the battery would be seen over the usage. So we will be mostly focusing on these are so many factors, and we cannot deal with all of them in one webinar. But we'll just go through some of them briefly. One of them would be temperature of operation. The other would be depth of discharge and rate of charge and discharge. How they are affecting at the physics level in a battery. So typically we use a mathematical model. We have some data. We use that data to generate a mathematical equation, and then we use that equation to predict uh, certain aspects of any system for that matter over life. How would it perform over life? This exercise of mathematical modeling is similar to what we used to the connecting the dots exercise when we were kids. Um, the only problem is in this particular case of battery life modeling, we are given only two data points: cycle life at some rates, and storage life at certain condition. So the data provided is very minimal, and we are expected to develop models which can really draw this elephant, uh, not just the elephant, but we need to predict the behavior of the elephant over time. So there is a data malnutrition in this particular field. That's where the models or the physics base of the model becomes very important. Uh, in the durability, so we are again talking about how long the battery lasts. So durability of the battery. In the durability literature, they commonly use a bathtub curve. So something like this. So this is time axis and this is kind of failure rate. So initially there are failures. These are infant failures and early failures. These do not typically come to the application engineer. These will be at the manufacturing side. The second would be the random failures or instantaneous failures. So things going wrong randomly. Typically for batteries, this number is very small. It's around 1 in 10 million or less than that, depending upon who's the manufacturer is. But if you are taking cells from good manufacturer, the random failures are really low. And then the third part is wear out failure, which is what the degradation is. So batteries gradually degrade over time, and then there is a distribution. So all the cells in a battery.
Rutuj, you have gotten muted. Unmute yourself.
So I don't know where I left. Can you? Did I talk about Bathov curve? Hello, can you hear me now?
Yes, yes, yes. You had started on that. Yeah.
Yeah. So basically, in the durability literature, people use bathtub curve. Give me a second. Yeah. Uh, Basically, this is time axis and there are failure rates. There are failures which are infant failures. These typically happen at the manufacturing locations. Then there are failures which are random failures. They are occurring throughout the life randomly. But for a good manufacturer, the random failure rates is low. For lithium ion batteries, this rate is less than 1 in 10 million cells. And then there is something called wear out failures, which is basically degradation of batteries over time. Again, the wear out failures in a pack would not be same for each individual cell. There would be a distribution of wear out, so there would be a mean capacity loss, but then mean capacity loss, and then some cells would see higher capacity loss and some cells would see lesser capacity loss. So our focus on this particular webinar is again wear out failures, wear out mechanisms for lithium ion batteries. So they can be classified in two major categories. One is two major mechanisms. One is side reaction. So there are side reactions happening within the cell, which basically eat away the lithium inventory. It also results in gas generation, pressure buildup, or metal ion dissolution, resistance increase. So all these side reactions. And then second part is mechanical degradation, where the electrode particles or the SEI layer or the electrode laminates degrade due to electrode expansion and contraction. So we will look into all of these in the coming slides. Now again we have a cell, and then cell is made up of electrodes which are bundled together. So we see a positive electrode, negative electrode, and they are separated by electrolyte. Typically, the electrolyte solution is lithium iron phosphate, so dissolved in carbonate. So ethyl carbonate, diethyl carbonate, dimethyl carbonate. Now the problem is all of these carbonates or any solvent for that matter have a particular stability window. So they are stable in a particular voltage window. For example, these carbonates are stable between 1.5 to 4.3 at room temperature at storage conditions. The problem is our negative electrode has a potential of less than 1.5. It has average potential of 0.85 millivolts, whereas the positive electrode has a potential anywhere from 3 volts to 4.3 volts. So basically, the, the electrolytes are not at all stable on the negative electrode surface, and in some cases they are not stable in the on the positive electrode surface as well. So comparing LFP versus NMC, NMC has a higher voltage. The positive electrode voltage is even higher than the LFP electrode. So LFP is much more stable than NMC because the LFP voltage is 3.7 volts on the positive electrode, whereas NMC can go up to 4.1, 4.2, 4.3 volts. The result is the electrolytes, which are carbonates, are not stable, and they decompose on the electrode surface. So as soon as they see some electrode surface, they react and they form some inorganic compounds such as lithium carbonate, or they may form compounds such as gases such as ethylene or carbon dioxide. So various reactions happen. These are side reactions or unwanted reactions. The result of these reactions is basically the electrode particle, which is surrounded by the electrolyte. You would see as soon as you form this cell, there is a layer of compounds or reduction products that are forming around the electrode particle. This layer is called solid electrolyte interface, or SEI. So this is similar to oxidation of metals when they are in air. So there is oxidation layer on, let's say, iron or copper if you just put it in normal air. So these are similar products which basically form a layer. Now once a layer is formed, they basically reduce the rate of reaction because there is the distance between. So they kind of form a passivating layer. So the electrolyte is not in direct contact with the electrode anymore. So they reduce the rate of reactions, but the rate of reactions is not totally stopped. So these reactions basically continue over the life of the cell, and the thickness of this layer gradually increase over time. So what happens is, as these reactions are happening, more and more lithium is being confused. So this is the leak that we were talking about in the previous example. So these reactions are acting like leak, and they are basically eating away all the lithium from your system. The so the solid electrolyte interface layers, this SEI layer tend to grow over the age of the cell continuously, whether you're storing or where we are using the cell. So there is a degradation over time. Now the rate of these reactions is temperature dependent, like any other reactions. So higher the temperature, higher is the rate of reaction, and typically they follow something called Arrhenius behavior. But what it means is you will have much higher degradation at 45 degrees Celsius than 25 degrees Celsius, and much higher at 60 degrees Celsius than 25 degrees Celsius. Whereas you will have lower degradation at 0 degrees Celsius when you just store the cell. Again, these are all example numbers. They may not apply to your particular cell. But now in real life, when we are designing our cars or vehicles, there is a variation of temperature throughout the life. For example, this is the blue curve is Phoenix temperature in USA throughout. So throughout year and then 10 years. So it's repeated over 10 years. And orange one is the temperature of ambient temperature in Detroit. Now, if you just store a cell, this particular cell, in Phoenix or in Detroit, you will see that you will have different degradation. So Detroit one will have much lesser degradation, whereas Phoenix one will have much higher degradation because Phoenix has higher average temperature. And in this degradation pattern, you will see that there are waves. These waves are being formed because of variation in temperature. Now, the same principles would apply to any designer who is designing here in India. We'll have to look at what is the ambient temperature change over the year for that particular location where your user is going to use the vehicle. Again, this is just ambient temperature, and the assumption is the cell is following the ambient temperature exactly. Whereas in real life, your cell would have additional heat generation when you're using it. It may have longer thermal constant, so it may take long to cool down and stuff. So cell temperature could be very different than the ambient temperature. So you'll have to look at the cell temperature rather than the ambient temperature. The important aspect of this understanding is that you will get different life when you are using your cells at different temperature conditions. And this could be used to basically find out what's the temperature limit that you would want for your system when you are designing your thermal management system. Basically, how long you want your battery to last and what kind of temperature would it see over the life of the cell. So we talked about the ambient temperature, but there is second aspect, which is what kind of speeds your vehicle you want to use and what it means to the battery. So you can take a usage profile and find out what's the power requirement from the battery, what's the current delivery from the battery, and based on your thermal system, you can look at what's the temperature that your battery will see over time. So this is the plot on right is basically temperature for this particular cycle. And the idea is you design your cooling system, whether it's air cooled or liquid cooled, such that you can basically remain below a certain temperature, let's say 45, 55, whatever you choose, the maximum temperature you would like. Your cooling system should basically keep your cells below that temperature when you are using it, and that can basically prolong your life. So basically, thermal management needs to understand what's the temperature limit for meeting your life requirement, and then what's the size of your cooling system to keep it within the certain limits. Next part is battery cycling. So we talked about battery storage, what is happening during storage, but second part is battery cycling. Again, to recap, lithium-ion batteries have lithium ions which are being transported from one electrode to the second electrode continuously as we charge and discharge the cell. So again, lithium-ion batteries are intercalation batteries, or the electrodes are intercalation electrodes. What it means is lithium ions will be diffusing inside the particles of your electrode. Now, whenever a host particle gets an additional lithium atom, the thing that will happen is whenever you lithiate your electrodes, so assume that these are electrode particles, these circles, and these are lithium ions. And when you start intercalation, you would see that your particles are expanding, and when you deintercalate, your particles are contracting. The color change is also there in certain cases, but that's not of reference here. So as we charge and discharge our cell, lithium ions basically go inside the electrode particles. The electrode particles may expand, and when you deintercalate from those particles, your electrode particles will contract back. For example, graphite electrode will see about 10% expansion on complete lithium. Whereas if you want to use silicon as your electrode, for your information, silicon has much higher energy density than graphite. But the problem with silicon is it has 300% expansion. So your cell may be much bigger when you charge the cell than when you discharge the cell. So there is this continuous expansion and contraction happening within the electrodes, and this is called electrode breathing. Now there are several effects that are happening as a result of this electrode breathing. We'll go through some of them here. So the first effect that happens is, remember we talked about electrode particle and there is a SEI layer around the electrode particle. Again, this SEI layer is typically
Rutuj, we lost audio. You're not audible. Rutuj? Rutuj, can you hear me? There seems to be some bandwidth issue or the internet connection issue.
yeah. I'm sorry. Yeah,
Are you here?
going through the load shedding phase, right? Yeah. Can you hear me? Hello.
Yeah. So the screen is gone, but
Yeah. I'll share.
you need to reshare.
Yeah, you can. Yeah.
Can you see it now? Okay. Give me a second. Yeah. Can you hear me properly? Hello.
Yes,
Yeah,
yes,
you're
go
audible.
ahead.
Yes,
Yeah.
we can. Sometimes there is some kind of like a masking effect which we see in your voice.
Oh, really?
Are you using
Okay.
headphone? Or?
No, I'm not actually. I'm just
So
using
let's
my,
continue, no problem.
yeah. I'm just using my computer. Anyway, yeah, we'll see. So, yeah, going back to our electrodes. So remember, our electrodes are surrounded by or have a coating layer around them of SEI, solid electrolyte interface. Now, when your electrode particle expands, like what we showed in the previous image, uh, first thing that will happen is there would be a lot of stress generated on this coating layer. Basically, this coating is not expanding like your inner particle is, and this coating may break. So as soon as the coating layer breaks, there is much more electrode surface exposed to the electrolyte. So electrolyte basically seeps in through all these cracks and forms and performs more side reactions. So there are more side reactions happening on these exposed surfaces. So this more side reaction will result in more capacity loss. That's why we typically see more capacity loss when we are cycling than we are storing it, and even if we are cycling at low rates. So this is just an expansion contraction effect. We can, of course, model it. I don't want to go into details of the model, but you can basically combine the diffusion equation with the stress equilibrium and find out what's the stress that this particular SER layer would experience when your electrode is expanding, and what it means to the capacity loss. It turns out that we could find that the capacity loss is actually proportional to square of depth of discharge over the length of SEI. So this equation is very important, and we could patent it. There was a publication around it too. Um, it is important because now we can predict how many cycles a cell can do for various depth of discharges, even if we don't have data. Remember, we have scanty data, we have very limited data of charging discharging, and we still need to understand how our cell will perform in a given situation. So for example, in this particular case, we had only two data points, the yellow circles. We used only two data points, and then this is the red circles are the experimental points, and then blue are the model estimation. But we see until at least 20% depth of discharge, we could predict it very accurately based on a physics-based equation about number of cycles to failure for a given depth of discharge. Now, why is it important? Because depending upon the application, whether it's a full hybrid, whether it's a plug-in hybrid or a battery electric vehicle, BEV, or pure electric vehicle, we may need to, our battery may need to undergo different number of cycles. Say, for example, the US ABC, the US Advanced Battery Consortium, has a target cycle number for FHEV is 300,000 cycles, whereas for PHEV it's about 5,000 cycles in the charge depletion mode and 300,000 cycles in the charge sustain mode, and for BEV it's 1,000 cycles. Again, this is long range BEV. So we need to know what's the DOD that we can use for meeting particular number of cycles, and that's why this equation become very critical, and we could and we patented it at Ford. Going to the second effect of cycling, typically this second effect you would see it when you have large C rates of operation. So you are charging and discharging at relatively larger C rates. Again, the large is very subjective term. For example, for power cell, even 2C, 3C may not be large C rates. For an energy cell, even 0.5C or 1C could be a large C rate. So it's a cell design specific term, but we will have to look at C rate for large C rate for that particular design. What people found is when they try to cycle the cells at higher C rates, they will see the electrode particles cracking inside. So the electrodes are made up of these particles which will break over time, and typically they will see it at higher rates and lower temperatures where electrode particles will totally pulverize. So we wanted to understand why would it happen. Going back to physics, basically when we are charging and discharging, again we are lithiating from the outer surface. So as we lithiate, there would be higher concentration of, if we assume that this yellow is the lithium concentration, there would be higher concentration of lithium atoms outside, and these lithium atoms would gradually diffuse in towards the center as you lithiate. So there would be, initially there is no concentration, then there would be a concentration gradient. What it means is there is higher concentration outside and lower concentration inside, and then the concentration gradient would be different at different stages of usage. Also, it will depend on the diffusion coefficient of your electrode and stuff. Now, why these concentration gradients are important? Because these concentration gradients will create stress. What kind of stress? It's called diffusion-induced stress. So diffusion-induced stress are very similar to thermal stresses. Probably many of you know thermal stresses. If you have metal plate and if you heat it from one side, if you have higher temperature of plate on one side than the other side, so you have to heat it quickly. what you will see is the metal plate bends. That's because the side which is warmer expands more, whereas the side which is not yet warm would not expand as much. So to maintain the continuity, the metal, there would be thermal stresses happen, and then the metal plate will bend over time. And then you can use Hooke's law to calculate the stresses in thermal expansion. Similar thing is happening here in diffusion case. So as your lithium atoms are diffusing in your electrode, there is higher concentration of lithium atoms on one side of the electrode, whereas there is lower side on the other side. In this particular case, there is lower concentration at the center and higher concentration at the surface. So the surface part wants to expand more, whereas the inner part, which doesn't have enough lithium concentration, does not want to expand at all. But to maintain the continuity of surface, there would be a compression on the outer surface, and there would be a tension on the inner surface. So there are these stresses happening, and these are diffusion-induced stresses. And then you can calculate how much would be the diffusion-induced stress when you are charging and discharging your battery at a particular rate. Again, higher the rate, higher would be these stresses. Now you can basically calculate the diffusion induced stress at different times. For example, this is 0.01 normalized time, and this is 0.4 normalized time. So at different location within the electrode particle, you would have different stresses. So there are positive stresses, which are tension, and there are negative stresses, which are compression on some part of the electrode particle. Now, each time you are charging and discharging your cell, each of your electrode particle is seeing some positive and negative stress. So there are tension and compression cycles that it is experiencing. And if you go to fatigue mechanics, every material can sustain certain fatigues, certain stress for so many number of cycles. So this is basically the number of cycles to failure for a given stress you can know from fatigue mechanics. So similar principles could be applied on electrode particles, and we can know basically how the electrode particle, how much stress the electrode particle is suffering, and what it means to the particle. So higher rates, higher would be the stresses. Lower temperature, again diffusion becomes slower, and then the stresses become higher. So what's the implication of these stresses? So the electrode particles may gradually crack. Now there is this electrode particle, and then there are always some defects to start with on a particle. And as you are doing charging, discharging, these micro cracks will gradually grow. Now what happens is, whenever there is a crack, new electrode surface would be exposed to the electrolyte. So electrolyte can just seep in this crack, and it will react on the surface and then basically form new SEI or have more side reactions on this surface. So there is more loss. So it's this kind of degradation is called coupled chemical mechanical degradation. Remember, if there was only mechanical degradation, it may not be as bad. But since we have these chemical reactions which are eating away lithium from the system, it becomes more harmful. So you can use, say, classical Paris's law to understand what would be the crack growth in the electrode particles. And based on that, you can come up with some equation which will tell you how much would be a capacity loss if you are charging and discharging the cell at a particular rate of operation. So we could use this equation on a A123 data, and we could basically fit the data very well based on the physics again. So this is third type of degradation mechanism basically happening within the electrode particles. Now there are additional degradation mechanisms such as lithium plating. So if you're trying to charge your cells at really high rates, specifically when you're already close to fully charged, so your higher SOCs, higher state of charge, if you're trying to charge your cells at high rates, you may see that the lithium Rather than intercalating, it will just plate, it will just deposit on the electrode particles. And as soon as it deposits, it basically reacts. Hello. Divankur, can you hear me?
There was some noise. I don't know. You can continue now.
Okay. So yeah, so I was talking about lithium plating. So this typically happens when you're um, so those could be additional degradation mechanisms. The other could be cell swelling. So each time you're charging and discharging your electrode, the electrode particles are swelling. That means the entire electrode is swelling. That means the cell will swell, but cell will contract down. Maybe this cell expansion and contraction may not be as elastic as you would want. It could be a plastic expansion. Additionally, there are a lot of gases being generated, especially when you're using your cell at higher temperatures or higher currents near the high SOC ranges. So that's where you will see these cells ballooned up, especially pouch cells and prismatic cells, you will see more. Um, then there could be mechanisms such as non-uniformity in cooling within a cell or within a pack. Certain part of the cell or pack could be at higher temperatures, the other parts could be at lower temperature, and there is non-uniformity in degradation because of current distributions. At the pack level, you may see that there is a mean degradation or average degradation you have, but there is a distribution around the average distribution. So you have to understand what is the distribution, because in a pack, if all the cells are in series, then the cell which is weakest or has least energy would decide the energy of the pack. So basically you need to understand the distribution. Again, the better quality of cells means lower distribution, so lower 3 sigmas around the mean. So all these factors could come into play depending upon your particular application. So in the end, we can basically develop a simple life model. For moderate operations, you just need to understand these 3 physics principles. One is the side reaction that are continuously happening. You have to basically put it in the mathematical equation. Then you have SEI cracking, which is continuously happening as your electrodes are expanding and contracting. And there is a particle fatigue, which will happen only at higher rates of operation. So your typical battery model would look like something like this. Your input would be either vehicle speed or power requirement from the battery. The temperature, this temperature could be just the ambient temperature, and then initial SOC. And then you will run your profiles for 1 year, 2 year, or 10 years, whatever your target life is, through an equivalent circuit model, which will basically tell you what's your state of charge, what's your voltage, what's your current from given speed or given power. And then you will use that to understand what kind of effect that current is having on SEI cracking, side reactions, or particle fatigue. And combining all of these, you will find out what's the new capacity or what's the new resistance in your cell. Again, resistance part I could not cover in this particular webinar, but we can calculate that. And then there is a feedback loop. So basically, whatever capacity degradation you have calculated would also affect your next time point equivalent circuit model. So or any thermal model for that matter. So there is a loop around it. So the idea is your input would be speed and temperature, and your output would be capacity retention for different locations. For example, you can put different locations, temperature conditions, and usage conditions. So that's the big battery life model we can generate. And basically, this model will tell you how long your EV battery lasts. I won't be able to tell you right now. So again, coming back to the original question, how long would an EV battery last? answer, it does depend. Depends on your quality of cells, the characteristic of your battery pack, and the usage profile. You are expecting what's the 90th percentile or 95th percentile or 99th percentile customer usage that you would expect, and based on that you can design your batteries. Can one estimate the life? Yes, definitely. If we follow the physics, we can definitely come up with simple equations that can tell you how long your battery is going to last. Again, principles of physics are universal; they are not going to change. And as long as you know the mathematics, which is language of physics, you should be able to predict the or estimate the life of your battery. At last, I feel like any battery life modeler is like a astrologer, and we are trying to predict the things happening in life of this battery balloon. I think that's where I will stop. If you have any questions, you can go ahead. Thank you.
Yes, Rutuj, thank you very much. That was really a good insight which we had on battery life. So there are some questions which we have been getting since the start of the webinar. I have just consolidated them and we'll go one by one. So the first question was, what are advantages of sodium ion battery over lithium ion battery?
That's not related to the
Yeah.
topic we are aware of. But okay, in general, what are the advantages? I really don't know. Probably for automotive purpose, sodium ion batteries are not ready yet. They may come into future because their energy density is again lower than the lithium ion batteries, as far as I know. And they are not there for commercial. So commercially, they are not available for automotive applications as of now. I don't see things going to that direction right now, at least next 5 years in the automotive world, unless you come up with some applications which are low rate applications. Right? Yeah. Advantages could be, of course, the low cost, much lower cost probably. Right.
Yes. The second question is make clear on DOD if we are using 50% of total capacity and again we are charging means what kind of deformation. Okay, so the question seems to be about if the charging and discharging is happening only 50% of DOD, how would that affect?
Yes. So basically, lower the depth of discharge, larger the number of cycles it can go. So basically, you see the minimum number of cycles it will have is at 100% DOD, whereas at 50 it may have much larger number of cycles. Again, the scale is 10⁵. So if you look at the absolute numbers, you will see much higher number of cycles. So again, you can increase the number of cycles by reducing the DOD. The disadvantages is you are oversizing your system significantly. So when you are using only 50% of depth of discharge, that means your size of your battery is double that it would be when you are using 100% depth of discharge. So advantages and disadvantages both are there, right? It does depend on the application. If you are using it for storage application, then there might be cases where you would see a customer would use it only for certain DOD because that's how the load profiles are. But in automotive application, if you so for example, Tesla, if that's a 300-mile vehicle and a user is using only 20, 30, 40 miles a day, and you're using probably 10% of the total DOD, and you may see much large number of cycles on those cells. So when I say 1,000 cycles, those are assuming you're using full band of DOD. If you are using less number of smaller band of DOD, you would do much more number of cycles, and that means higher life, longer life, basically.
Yeah. So it is even longer even if we consolidate, like if 50-50 we add, and if it is 100 then consolidated also will be higher. So there are some questions on fuel cells, but I guess we can't answer them because the topic is not about that. Is it necessary to employ cells from the same manufacturing batch if you are, let's say, building a battery pack for an automobile?
Yeah, so it's better if you have cells from same batch, of course, same manufacturer, and then if you have them from same batch, that's even better. That's because there would be less variation within a batch, cell to cell variation. So when you put cells in series or in parallel, you would see if you have larger variations, your total usable capacity gets lower. Um, if they are in series, definitely the least capacity of the capacity with the cell with the least capacity would basically determine the total capacity. If they are in parallel, some of the effects are overshadowed, but still there are certain effects. You may not get the capacity which you would expect by just adding the numbers. So it's better to have cells from the same batch, or at least same manufacturer for sure. Same batch is better, definitely. And even within same batch, if you can look at um, uh, their variations and see that they are within a small band, that would be even better, right? You can, if you can look at, say, resistance parameters or whatever. Right?
Yeah. So the other question is, the temperature across globe is rising, and that we are seeing. We can have summers going as high as 45, 47 degrees centigrade,
Right.
taking 10 degrees rise because of the enclosure, etc. So under the hood temperature could be even higher. That's what the question means to say. Uh, would the would would that lead to cells going across 55 degrees centigrade? And in such cases, how to maintain the cells so that the battery life is ensured?
Right. Yeah. So yeah, I have seen specifically a lot of startups. The batteries I'm seeing, these are totally enclosed batteries, and if you don't have good heat transfer outside, then you would, and if you are using it at higher rates, then you would see that your temperatures, battery temperature rising to 55 or more than 55. You definitely don't want to use battery after 60 because it may go under runaway reactions. That's not safe. So it's definitely important to monitor your temperatures and then have a control system which will allow you to not use, or allow or not allow you to use the battery after a certain temperature. Now, how would you reduce the temperature? Again, you need to have good cooling system. Let the airflow cooling. If you have air cooled system, then it could be active air cooled rather than passive air cooled if necessary. But keep on monitoring your temperature for the 90th or 95th percentile customer. So the harsher usage of your cells, so that your no, none of your customers would have a battery which would go into runaway, which would go into much higher temperatures than 60, let's say. Um, Again, the original question was, how do we reduce the temperature? Again, I think the answer is cooling system. I won't be able to tell what cooling system your particular system would need, but cooling system is definitely needed. Again, there are two parts. One is temperature during usage, and then there is temperature during parking as well. So if you have good air circulation, then your battery may reject heat more quickly, and it may not stay at higher temperatures for a long time. You want to minimize the battery temperature even when it's parked, or when it's driving. Right? I hope that kind of answers your question.
Yes, yes. Uh, what is effect of low temperature on battery which is discharged to 20 percentage or lower? Can it deliver the same energy when it is again fully charged?
Yeah. So if a battery is just, if you just cool down the battery to, let's say, 0 degrees Celsius as well, or minus 20s, minus 30s, and you do not do anything. So if you are not using the battery at those temperatures and you just bring the temperature back to 25, lithium ion cells would not have any effect at all, or have very minimal effects. if you are using the cell at lower temperatures, at 0 or below sub-zero temperatures, then you have to use it mildly. You cannot use them at the same rates that you would use them at 25 degrees Celsius. And this would arrive especially in North India, where the temperatures tend to go lower. Uh, me coming from Detroit, where the temperatures would always be around 0 degrees Celsius in winter or less than 0 degrees, we had to be very careful of battery usage below 0. So you may not be able to deliver the same power. You should not be able to use, you should not use the battery at the same rates at lower temperatures. But if you are not using the battery at lower temperature, you're just cooling it down and then heating it back to 25, it should not affect anything. So remember right. So this particular plot I wanted to show. Yeah, so at 0 degrees Celsius, the reactions are happening at very low rate. So there is no side reactions happening practically at 0 degrees Celsius or any temperature below that. So there is no worry about degradation. In fact, if you want to store, have a battery after 10 years, use the battery after 10 years, you just store it at 0 or -10 for 10 years and nothing will happen. The battery will remain the same for those 10 years and you can use it after 10 years. It won't affect at all. Right. But if you are charging and discharging at those conditions at higher rates, that's a huge problem. So, yeah, let me show this curve. Let's see if I have it or not. Yeah. So basically, so battery life, there is a sweet zone of operation specifically between 15 to 40, where battery likes to be. If you are going lower temperatures and using it, it's not good. You will have much faster capacity loss. Again, higher temperatures, you would have capacity loss. I think that answers the question.
Yes, yes. So the next question is about ACI layer thickness. How much? What is the typical ACI layer thickness, and how long will it take to achieve 1 millimeters of thickness? So I guess the thickness is in nanometers, right? It is very, very small.
Yeah, it would be around a few nanometers to start with and grow up to say maximum to 1 micron, 2 micron. So it won't, or few microns, few tens of microns at max. It won't go to millimeters at all, right? So the cell expansion is not happening because of SCI. SCI, the cell expansion, if the question here is basically he's thinking that cell expansion would be different due to SCI thickness. That's not true.
Okay. Can you repeat the point regarding capacity loss versus DOD in short?
Yeah, sure. Yeah. So, yeah, so basically, depth of discharge will tell you how much your electrode is expanding and contracting each time you are charging and discharging. Larger the expansion and contraction, more would be the capacity loss. In fact, for a given cycle, a capacity loss in that particular cycle is proportional to square of depth of discharge. It's not true for all the cycles. I mean, it's not constantly proportional. This relation is changing, but given in a given the capacity loss in a given cycle would be proportional to square of depth of discharge. So higher the depth of discharge, more will be the capacity loss. Does that answer the question?
Yes, yes, it answers it. The next question is, how much is the discharge rate of lithium battery when it is not being used?
Oh, you mean self?
So what is the self-discharge rate?
Yeah, those I think generally manufacturers give these numbers. They are different for different manufacturers, but in general, in principle, batteries have really small self-discharge rate. So
Your voice is not clear.
okay, okay, yeah, and I was saying these numbers typically the manufacturers would give these numbers because it does depend on the particular cell and the additives it has and stuff. the electrolyte additives it has. But in principle, lithium-ion batteries have really low self-discharge rates. So you can have a battery stay there for years, and it may not lose much capacity. Depending on how much, there may not be a lot of self-discharge. Right?
Yeah, so we have some LFP cells lying at our office, which are there from last 3 years, and nobody actually had touched them. And when we took it out of the stock, they were still performing well. Not up to the mark, like not to the full capacity, but they were still performing.
So there are two things, right? One is degradation that is happening continuously, and there is self-discharge. So
Yeah,
self-discharge is kind of recoverable capacity, in addition
yeah,
to the degradation, right?
yes. So the voltage was also like around 3.2 for them, which
Right.
is again typically seen in these LFP cells. Okay, so the next we have similar type of questions in some further questions also are similar, which are dependent on particular cells. But let's try to answer them. What is the maximum C rate possible for charging in EV batteries? Again, this I guess depends on so many parameters, but you can try to answer it in brief.
Right. So typically the energy dense batteries, which are used for long range electric vehicles, at least for electric cars, those have low higher C rate. So they can handle maybe up to 1C, 2C, maximum 3C instantaneous C rates. If you look at batteries which are used for hybrid vehicles, full hybrid vehicles specifically, the batteries can handle up to 15C, 20. I've seen batteries handling 20C instantaneously, and higher, maybe 5C, 6C continuously. So it really depends on the electrode structure for that matter. So how densely your electrode is packed. So higher energy density, that means all the electrode particles are close together. If you want higher power density, then you will have to separate these particles out. So you will have more porosity for lithium ions to travel, and then you would get much higher C rates that the battery can be used at. So it does depend on the battery design or the electrode design.
Yes. The next question is about again ACI layer formation. The question is talking about are there any coatings available which can counter ACI layer formation? But I guess I need to rephrase that question. Are there any additives available which can counter the ACI layer formation?
Yeah. There are large number of additives available. For example, vinyl carbonate or FEC. So, but again, the additives of each company are the secret recipe. So why, let's say, a Panasonic cell would work better than some random cell supplier? Um, I don't know if it does or not, but if it works better, that's because they have better recipe of additives. They can put large number of, they can put the right additives, which can form a good SEI layer. And now this SEI layer is more passivating. It doesn't mechanically deteriorate as much, and then you can get much better cycle life. Again, life of your battery is totally dependent. I mean, SEI layer is the key of battery life. So if you can put the right additives, if you know the right additives, you can your cell can last longer. Even for higher temperature, I have seen cells which are performing better at 45 degrees Celsius than at 25 degrees Celsius in storage. That could be just because the additives are such that they react quickly at 45 and form a good layer around the electrode particles. And now you have, and about coatings, there are experiments being done where they are trying different ALD coatings, so atomic layer deposition coatings on the electrode particles, and some of them have shown some success. Um, I haven't seen um, anything of that sort at the industrial scale being used at this point. Right. Of course, they
And
use
obviously all these things will also increase the cost of the cells.
exactly. So all the many good manufacturers use ceramic coatings on the composite electrode. So the total electrode, not the particle at the particle layer, but at the composite electrode level, they may put a ceramic coating. Um, but that's so some of them do that. Not all of them do that, right?
Yeah. So there is another question about why does battery reduce its capacity when it is used at higher power? I guess we have answered this question throughout. So the whole session was about that, right?
Right. Yeah. Yeah.
So
Then I'll
we'll take the next question.
go through it again, right? The entire course.
How lithium titanate supports fast charging without a heavy degradation when compared to LFP or NMC cells?
Right. So lithium titanate is a crystal. So similar to. So no. Lithium again. Even lithium titanate can have LFP or NMC electrode. So lithium titanate is a negative electrode. The positive electrode can be same LFP or NMC. It doesn't matter. So the thing about lithium titanate is it is crystalline structure like LFP NMC, and it has much bigger um, space for lithium ions to go in and come out. So it has basically three-dimensional channels for lithium ion to go in and come out. So it doesn't have any expansion at all. Whereas graphite, which is normally used, has 10% expansion. Lithium titanate would not have any expansion. The other positive thing about lithium titanate is the voltage of lithium titanate, the potential of the electrodes is 1.5 volts. So we looked at the stability window of the electrodes. So our normal graphite electrode is much lower than 1.5. That means reduction reactions will happen on that. But lithium titanate is very close to 1.5. That means the rate of side reactions is minimal, or there are no side reactions theoretically. So that also gives much longer life than, let's say, a graphite based cell of NMC or LFP for that matter. The only disadvantage is, of course, cost and energy density. Since your negative is at 1.5, your cell voltage becomes much smaller. Whereas in case of normal anodes, the negative electrode is close to 0 or 0.085 volts. So that gives you much bigger window of cell voltage, right? Yeah, bigger cell voltage.
Okay. The next question is about, so the question is asking us to show effect of any curve which can show effect of temperature on capacity. I guess many such curves are available. If you just Google this term, effect of temperature on capacity, you'll get so many curves. But if you have anything ready-made or already in the PPT, you can show us.
Right. No. The thing I wanted to tell is basically you may get any curves from the literature from Google, but it may not be applicable to your particular chemistry
Right.
or cell you are using. So you cannot just take one curve and then apply it to the other. You have to have some data, or at least data from similar cell. Again, when I say data, you can basically back calculate the activation energies, and that's how you should know the capacity retention of a cell at that particular temperature. Right? Yeah. So no ready-made curves or all the
Can you
batteries.
speak a bit? Can you speak a bit about internal resistance of cell? In short, like
Sure.
in a minute or so.
Yeah. So internal resistance of a cell has two aspects to it. Let me go back to any window for that matter. Okay, so just wherever there is a cell. So your lithium ions need to travel from the electrolyte to the electrode. Now there is one aspect of internal resistance which is traveling through the electrolyte, so the conductivity of the electrolyte. The second aspect, or maybe I would have a slide. Give me a second.
You had a slide where this circuit model was shown, equivalent circuit model was shown.
Okay, that's fine. Right, I can use this right here. So basically, electrons are traveling through the conductor, and they are going to the reaction sites. Whereas lithium ions are traveling out from the electrode particles through the electrolyte to the other electrode to the reaction site, and then diffusing in. So there is an electronic transfer. So there is a conduction of electrons from the conductor to the reaction site. There is a resistance associated with that. Then there is a transport of lithium ions from one side of electrolyte to the other side of the electrolyte. So there is a voltage drop associated with that. So there is a resistance with that. Then there is a resistance in form of rate of reaction. So only so many lithium ions can react at a time. So there is a voltage drop for the electrochemical reaction, and then there is a diffusion of lithium ions from the electrode surfaces to inside of the particle. So solid state diffusion. So all of these basically result into the resistance of a cell. Now, if you let me see if I have a circuit model somewhere. Okay, so all of these basically processes have their own characteristic resistances. Some of the resistances are purely ohmic. That means they happen instantaneously, whereas some resistances grow over time. So they have effects similar to a capacitor. That's why people use So people use RRC circuit to really calculate resistance of a cell. So it's not a single value resistance. So the single value that manufacturers provide are at a particular condition, that it's a 10-second charge pulse resistance. The resistance is continuously changing over time. Again, as the cell ages, the resistance may increase. In fact, so in some cases, it may first decrease and then increase, and it has to do with the formation of SEI layer, the electrode expansion contraction, the plasticity of electrode expansion contraction, and the things like gas generation. All of those things would affect the resistance change over life. But at one point in time, your resistance, there are two aspects. One is instantaneous resistance, and then there is this something called polarization resistance, which grows over time and reaches a saturation.
Yeah. The next question again is about somewhat like, what is the maximum C rate for charging EV batteries for a DC fast charger? So let me just answer this question. This one is maximum C rate for charging of EV batteries is dependent on which cell you are using, which manufacturer's cell, and depending on what is the C rate given for a particular cell in its specification sheet. Apart from that, how good is your thermal management for those batteries? Again, another question is similar: percentage drop in battery life due to regen braking. This again depends on how much energy is available through regen and what is the C rate, which is means it is boiling down to. And based on again that C rate, the percentage drop in the battery life can be calculated. I guess Rutuj, you can answer the next one. What is the what is difference between power cell and energy cell?
Yeah. So let me add one thing on the regen thing.
Yeah.
Regen, the capacity loss due to regen would also depend on what SOC, state of charge of your battery, are you doing the regen. So you are already at 90% state of charge, and then you are trying to do high current regen. You may end up lithium plating there. Whereas if you are at 20% state of charge and you are trying to do regen at the same current, may not be as bad as the first case. So yeah, again, the SOC would play a critical role. Secondly, the other thing about charging is what kind of charger profile you have. Is it it is continuous constant power charging? Is it constant CCCV charging, or is it step charging? There can be multiple charging profiles, and one profile can be much better than the other profiles, right? Yeah. Sorry. Now you can ask the next question.
Yeah. The next question is what is difference between power cell and energy cell?
Yeah. So energy cells tend to have much higher energy density. That means so going back to my first figure, so my battery has this huge circle, right? So certain cells have lower energy density than the other cells. What it means is the other cells may have much higher packing of much dense packing of electrodes than the power cells. So power cells can accept high C rates better than the energy cells, but they have lower energy density That means your range of your vehicle would be lower if you are using power cells. So typically for hybrid applications, they are more worried about providing power during acceleration or basically accepting energy during regen. So they use power cells for purely hybrid vehicles. Whereas purely electric vehicles, we are more worried about the range of your vehicle. So you tend to go with higher energy density cells. I hope that clarifies. Hello.
Yeah, Rutuj. So the next question is a little bit innovative. Can we have breathing in cell to reduce gassing?
What I do not understand what does it mean.
So what it says is, can we make the cell open so that it breathes, and that's why the gassing problem will be solved.
Right. Sure. As long as you do not allow any other gas to go in. If you are just taking out gases, that's not a problem. If you allow oxygen or nitrogen to go in during your breathing, then that may kill yourself quickly, right away. So all these cells are hermetically sealed. There is no way a gas can enter outside. Air can enter in a cell. Uh, you can take out gases from a cell, but as long as you doesn't allow anything else to go in, that should be okay. The other problem with the gassing is when you have generated all these gases, that means you have already eaten away all the some of the electrolyte. That means some part of electrode may be just dry. There is no electrolyte around it, and that could be another problem with gassing.
Recently, there have been a lot of talk over solid state batteries and glass batteries. Can you throw some light on that? Because we have so many questions which are about those kinds of batteries, solid state and glass batteries.
Right. Right. So I'm not an expert of solid state battery, but the information I have or the understanding I have is basically solid state batteries are similar to lithium ion batteries, except the electrolyte is no more liquid; it's a solid electrolyte. Good part about it is the liquid electrolytes are flammable. Then we have to care about safety and stuff. With solid electrolyte, you don't need to worry about that as much as you would need to. So the cost of the battery pack would go down significantly if solid state batteries work. Again, so solid state batteries have huge potential. They are very close to commercialization than any other chemistry apart from lithium. So if you want to ask me what is the next chemistry that will come in automotive, I'll say solid state batteries. Again, the chemistries are same, just the electrolyte is different. It's solid state electrolyte. But when I say next, I'm still looking at 7 years, so 2027 or beyond that. Not anything before that at large scale on the automotive automotive applications. So currently again the solid state batteries are in the research phase. They can be cycled. The only problem is currently the electrolyte is not mechanically as stable as you would want, and there are things like dendrite formation and short circuiting happening. Also, there are issues with the solid to solid connection. You have solid particles and then the solid electrolyte. Solid electrolyte does not have good wettability to the electrode particles. So the connection may not be as good as you would have in the liquid electrolyte. But yeah, so these problems are being solved in the research. They are still in the research phase. It may take some time before they can match the performance of lithium ion batteries.
Yeah. The another question is about DoD. So let me just read out the question as it is. For cell testing based on your experience, what SOC range are actually used by users across the world? Like users do not go to 0% SOC when they are discharging, and they would recharge generally at or kind of stop discharge generally at 20% of SOC. So what is your experience, as in at what number should they stop, or at what number generally the discharging is stopped?
No, yeah. So at what number should they stop? I don't think there is any limit. You can go to 0% DOD. There is no 0% SOC. So complete 100% DOD. There is no problem with these lithium-ion cells. Again, you have to define the 0% properly. But as long as your definition is correct, then there should not be any problem. The only thing is if you are at 0 DOD and then there is sudden acceleration, somehow your management system is not good and then you over discharge, that could be a problem. Now typical user behavior is they will stop using the vehicle when it's around 20% to 15%, depending upon how big your vehicle is. So I mean, what's the total range of the vehicle? But users do not like the range anxiety, so they will keep last 7, 10, 15, 20 miles just for safety purpose. So typically they would go down to that level if the application requires. Again, if we are talking about long range vehicles like let's say Tesla or Chevy Bolt or Ford Mach-E, you would see that users would use it only the top 20 or top 30% most of the time, because they would just drive 40 miles rather than 300 miles every day. So they are basically continuously charging and discharging between 100 to let's say 80 or 85. But that would be different for say Indian market, where the ranges may not be as big as 300 miles. Right?
Yeah. So I guess we have reached to our end of the discussion. So it's already 12 o'clock. Actually, 1 minute past that. So what we would be doing is we'll be consolidating all the questions together and we'll be answering them separately through emails. Because actually we are remaining with 30 more questions. We already have covered about 20 odd questions till now. So it will take another 1 hour to answer all of them. So we'll be answering them through emails. And I'll take this opportunity to thanks Rutuj and Shekhar. Are you there?
Yes, Durvankur, I'm there. And I've also shared my screen. So these are the members of the audience who have scored the top score on our quiz this morning. So Nikhil Madatil, Mahesh Warpe, Harshan, Sriram, Maruti, and Soham Wadhwa. You will be getting coupons of 20% discount on future courses from Device. The coupon will be emailed to you later today. Okay, so thanks for taking the quiz, and I also thank everyone who took the quiz this morning. We have had a very insightful discussion with Rutuj, and battery is a discussion point that will never end till the end of the battery. Right, so there is a lot of topics that can be further taken up as well. In the feedback form, you will get an opportunity to let us know what additional things you want to hear from us, and we'll try to cater a session for that. Yeah.
Yes. Also, if anybody has given a different email address during registration, and if they want the emails to be sent to a different address for the answers to these questions, you can post your email addresses in the chat box. Okay, so thank you very much, everyone, and see you again in the next webinar or in the training. Thank you all.
Yeah, again, I would like to thank you and all the. Thank you.
Thank you,
Hello,
Ratu.
Durvankur.
Yes.
Yeah, sorry, actually. Can we get the PPT of this webinar on our email?
Yes. We will email.
Yeah, thanks. Yeah, and if we can get the recording also, it would be helpful. Yeah.
Yes.
Yeah, thank you. Thanks.